the fourth of 10 conversations in which the late Jacob Bronowski related to George Steedman his personal account of the discoveries and philosophies of the 20th century. Last week, Dr. Bronowski discovered the word pattern, and this week considers the shape of pattern in The Structure of Energy. The program is introduced by George Steedman.
I hadn't realized that the quantum theory came so early in the century as a theory that things don't proceed by beautiful balletic movements, but by discrete jumps. Now you see it, now you don't.
And that is exactly as old as the century. That is, a conversation between Max Planck and his son took place at the end of 1899. He published the paper in which he first proposed that energy comes in discrete lumps in the year 1900. It was taken up by Einstein in that phrase about arrows of light in 1905 and became a well-argued, well-understood principle during the decade of 1910 onwards. Remember that the great advance in the structure of the atom, to which we must return later, was made by Niels Bohr in 1913 by putting in the quantum into Rutherford's model of the atom. The ideas of quantum physics were already vital to new ideas about the structure of matter by 1913. They reached their great climax, the uncertainty principle, in the year 1927, the year in which I went to Cambridge as an undergraduate, and Cambridge and Europe in general was agog with the new, what was then called quantum mechanics, between the years 1927 and the early 1930s. And it's those ideas that I'd like to speak about on this occasion. It had been recognized, as I say, from 1900 onwards, for more than 25 years, that the structure of energy is also lumpy, the way the structure of matter is. In other words, that there are units of energy which you cannot break apart into smaller pieces any longer. But just how to apply this knowledge had turned out to be very difficult. And as for what it meant philosophically, nobody had any idea at all. That seems a funny thing to say. Why philosophically, you know? What the hell has science got to do with philosophy? And the answer is everything. Science has become a powerful tool of the imagination in the 20th century, exactly because nobody is satisfied with any scientific discovery until they have answered the question, what does it tell us about the structure of the world, which gives it a new kind of inner arrangement, what you in our last conversation called inner pattern. Now, what is this pattern was what everybody was trying to discover all the time, from 1900 to 1927. And then in 1927, Werner Heisenberg, a young pupil of the German school of quantum physics, came out with a very strange idea. He said, the reason you aren't finding a pattern is that you are looking for the wrong shape in the pattern. You are looking for a pattern of which the components have an exact outline. That's a pattern which is all right in the large world. If you want a clock to go, you must have one cogwheel engaging another cogwheel exactly and pushing it round. And if the drawing isn't exact in outline, it won't work. But atoms aren't clock wheels, is what Heisenberg said. Atoms have a rather vague outline. There isn't a place in which the atom is at this moment. You can't ask the atom questions about space, time, speed, and all the other things we'd like to know at the same instant. Because it isn't a great big lump of a thing, the way that a clock wheel is. It is a small, shimmering, evanescent piece of material whose properties can't be inferred from that of clocks, because clocks are made of atoms, not atoms of clocks.
The model I find always to try to grasp this consideration of a particle as both an object and a waveform is the smoke ring. It seems to behave as if it were Heisenberg's model, because if you try to investigate it at all, it disappears.
And your analogy is right in two different ways. First of all, in fact, the shimmer that you see in a smoke ring is caused by the trembling of individual particles, and they tremble because they are bouncing about on the molecules of air which are sustaining them. That's called Brownian motion. It's been known since about the year 1825, but it's never been understood until recently, and it's one of the things that Einstein described successfully in 1905. Secondly, in atomic physics itself, the analogy of the smoke ring as being a map of the possible positions of a subatomic particle is a very real one, and was put forward by a great French scientist, the Prince de Broglie. I mustn't divert us from our main channel. Back to the fact that the atom is not a small form of a clock wheel or other massive object, but on the contrary, that clocks owe their solidity to the fact that they consist of literally millions of millions of millions of atoms. And once you shrink back to the size of an atom, then behavior becomes very strange, like your smoke ring analogy. How strange? That's the question that Heisenberg answered in what he called the principle of uncertainty. He said the following. He said, "It is a mistake to ask of individual atoms and their constituents such questions as, at this moment, where is it? And at this moment, where is it going and how fast?" Those are too many questions to attach to a particle as evanescent as an atom, which indeed can only be called a particle by courtesy, which combines, like your smoke ring, properties of particle and wave. The fact is, we realize that the world on that level is made up of things, in inverted commas, which are not particles and not waves, but are just exactly what we see. Atoms, electrons, packets of energy, condensed so tightly that they seem to have material properties. But they are not material in the sense in which the billiard ball, my hands at this moment, or other things are material. Then what can you ask of them? You can't make descriptions of them infinitely exact. You must allow every description to have a certain uncertainty. That's what Heisenberg calls it. I prefer to call it what engineers call it. I prefer to say you must let descriptions of them have a certain tolerance, by which an engineer means you mustn't say, is it exactly at milestone 101 on the road from Cairo to Suez? You must say, is it within 10 yards on either side of milestone 101, or within 100 yards, or within 1,000 yards? What tolerance do you give to this? Well, that's already a very profound idea. And the brilliant thing that Heisenberg did was then to show that what Planck had earlier discovered, Planck's constant, the minimum packet of energy, is in fact a precise mathematical measure of the tolerance that you can achieve, or what he called the certainty that you can achieve. But I prefer to say the tolerance, the area of light and shade within which you will find it.
A minimum step of smoothness that
Yes.
you can define.
That's right. And that step has a very curious property, which is that, all right, you want to fix the position more exactly. You want to say, well, no, it's nearer milestone 101 than you're saying. then you can do that, but at the expense of not being as precise now in your definition of where it's going next. You can either be very exact in where it is, or very exact in where it's going. But you can only trade off the tolerance in one against the exactness in the other.
I see some analogy between your atom and its uncertainty and the statistical behavior of an object. With, say, a crowd or a voting population, and then trying to define exactly the state of mind of the individual within it, which is much more uncertain than his behavior in a context.
It is right to say of large objects, such as watches, hands, microphones, that they are populations. They are assemblies of atoms and their subunits. And populations behave much more predictably than individuals. You know, that was already said by the German philosopher Immanuel Kant almost exactly 200 years ago, when he pointed out that every individual love affair seems to be the whole of the universe to the two people who are taking part of it. But the man back at the registry office has a very good idea that there are going to be more weddings near Easter than there are going to be near Christmas. And that's just how atoms behave. You see, we've really pointed to something in my head as against my father's head. These two heads that the two skulls that we're holding, which is very 20th century. That in the 19th century, the behavior of populations so much dominated the minds of scientists and of the men in the street, that individuality was being removed from science, and everybody thought science is the study of the unindividual, unpeculiar, very general. Now in the 20th century, we're beginning to realize, even with minute objects like electrons and atoms, that the most interesting thing about them is the way in which one is not doing exactly what the other is doing.
That was the late Dr. Jacob Bronowski in conversation with George Steedman.